I want to talk today about specific rotation, what it means, and when we're dealing with it and concerned about it. And generally, when we're talking about specific rotation, we're talking about compounds that exist as enantiomers. For instance, we can talk about carbone, which can exist as an S isomer, or its enantiomer, its mirror image, the R isomer. So we can have S carbone and R carbone. And one of the things about enantiomers is their chemical properties are identical for the most part. So if we look at the chemical properties of these compounds, and I really should have said physical properties because these are physical properties. So at 25 degrees they're both oils, they both have the same boiling point, they both have the same density, they both have the same refractive index, they both have the same solubility in H2O. So they're both identical to one another with regard to these physical properties. So is there any way we can distinguish between the two? When I have a solution, can I tell if I have the S carbone or the R carbone? Well, there's one thing we can look at that's different between the two. If we look at the specific rotation, for the S carbone, it's plus 61.2. For the R carbone, it's minus 61.2. So there is a physical property that's different between the two. And we're going to talk about what specific rotation refers to and what it means and how we measure it. But before we do that, I want to point out one other thing that's different between these two compounds. Their aromas are different. The S carbone has the aroma of caraway seeds, and it's actually isolated from caraway seeds, whereas the R carbone is found in mint, and it has the odor of mint. So our nose is able to distinguish between these two enantiomers, even though their physical properties are the same. And that's quite often the case in biological systems. Quite often biological systems are able to distinguish between one enantiomer and another. So what does this specific rotation refer to? Specific rotation refers to the rotation of plane polarized light. And in terms of the values, so the magnitude of this number represents the number of degrees of that this light is rotated. So something that has a rotation of 30 rotates light twice as many degrees as something that rotates at 15 degrees. The sign, the plus or minus, represents the direction of rotation. Something that rotates in the positive direction rotates clockwise. Something that rotates in the negative direction rotates the light counterclockwise. So, what do we mean by plane polarized light and rotation of the plane of polarized light? Well, let's look at some diagrams to see if we can figure that out. So, in this experiment, we have a lamp, a light source of some sort. It's usually a sodium lamp. And then the light passes through a monochromometer. That just means it only lets one wavelength through. But when that light goes through, it's oriented in all kinds of directions. Sometimes the wave's going up and down, sometimes it's going side to side, sometimes it's going off at angles. All the different possible orientations of the light are represented. We pass it through a polarizing filter, which lets only one of those orientations of light through. In this case, our polarizing filter is only letting through the light that's going in the up and down, vibrating in the up and down direction. So now our light is polarized. This plane polarized light passes through our sample cell. And when we have an enantiomer like the S carbone, the light will start, the plane of the light will start rotating. So you can see it turning and turning and turning. And the longer it passes through this cell, the more it turns until it reaches a detector that says the light in this particular case was rotated minus 30 degrees. And that's what we're talking about by the rotation of plane polarized light. Now, in theory, the R carbone would rotate at the same number of degrees, but in the opposite direction. Now, when we do this experiment, there are a couple of things that can influence the value that we record. So in order to measure our specific rotation, we need to account for these variables. For instance, if my solution is more concentrated, there are going to be more molecules there to rotate the light, so I should see greater rotation. Also, if my cell is longer, the light is going to have more chance to contact my molecules, so I'm going to see more rotation then as well. So I have to account for these things. And I account for these things using the following relationship. So this equation right here. And in this equation, if we specify what each of these things represents, this is the specific rotation. The T just stands for the temperature that the experiment was run at. The D refers to the wavelength of light that's being used by this monochromatic filter. So this is the number we're trying to find. This A measured is the measured value, what we read off of our polarimeter. This L here is the length of the cell, how long the cell is that contains our sample. And the units that we use on this length of cell measurement are decimeters. This is the only place in science where I know that the official unit of measure is decimeter. Next we have concentration. And our concentration is in terms of grams per milliliter. So if we take the measured rotation, we divide it by the length of the cell in decimeters. We divide it by the concentration of our solution in grams per milliliter. We end up with our specific rotation.